Hello, today we are going to look at exponential and logarithmic functions, and we're going to start by looking at exponentials. Now an exponential function, or a function where the variable is in the indice or the power, for instance y is equal to 2 to the power of x, so an exponential function is going to be where the variable, the x, is in the exponent, so it's in the power. That's what defines it, and that's where we need to recognize that we are. And anytime we see something where we have a variable up in a power or x up in a power, we're going to open page 21 in our log tables, and we're going to look at the rules and tools available to us on page 21 for doing these types of questions. And it's important we get used to opening up that page so that we are constantly enforcing that's my toolkit if I need to rearrange any of these types of formulas, as I will in the long run. Now, if I look at two examples here to give a basic feel for the shape of these functions, I can see that this is just a basic sketch. They don't wonderfully relate to our points, but they're fine for giving a feel for things. So our exponential functions rise up as we cross the y-axis. So we would have negative powers of 2 here, where we have negative values of x, and positive powers of 2 here. So we start to grow, and when we have 2 to the power of 0, we're going to cross the y-axis at 1. Now this is an important defining characteristic of kind of basic exponential functions. Any number to the power of 0 is going to be 1. So they're going to cross, just a pure exponential function like this, regardless of the base number, is going to cross the y-axis at 1. Its y-intercept will be 1, and that's going to help us identify more complicated functions in a little while. But I've given you a few points here to give a feel for where this diagram is coming from. So we have, when x is minus 1, we have 2 to the power of minus 1, which is a half. So down here would be down at x is minus 1 and y is a half. And we can see when x is at 1, we'd be up at 2, and then when x is 2, we'd be up at 4, which would be somewhere up here. So we can see how our function is going to rise up over time. Now, what would happen if we had a larger base number? Well, if we had a larger base number, if we had 10 instead of 2, when x was minus 1, we would be way down at a tenth instead of being at a half. And when x was 1, we'd be all the way up at 10. And when x was 2, we'd be way up at 100 instead of just being at 4 like we were for powers of 2. So if we have a larger base number, it's going to make our function look way more abrupt. It's going to kick way, way quicker, way up, and increase incredibly fast. So instead of being a fairly gradual curve up like this, we're going to end up with something that's very, very close to 0 and then kicks straight up very quickly. So that's how you can identify higher base numbers. If we have a fairly gradual curve, we have a fairly low base number. If we have a higher base number, we're going to have a very abrupt change from very, very small, close to 0, way up. Now, something else to notice about this is our functions, if we think about it, there's no power of x that we could put in that would result in a negative y. So our range here, our range for our functions, our exponential functions, basic exponential functions, is going to be the positive real numbers, or the other way of putting that would be y greater than 0. So that, another way of putting that is to say that the x-axis is an asymptote, which I can write in here. So the x-axis is an asymptote. Our function going back into the negative x numbers is going to get closer and closer to the x-axis, but it will never actually hit the x-axis. And that will be true of any basic exponential function. Obviously, we could add or subtract numbers that would lower this function. So if we had 10 to the power of x minus 3, then we drop the whole function, and then minus 3 would be our y is equal to minus 3 would be our asymptote line, because we've lowered all of our y values by 3. But with a basic exponential function, we would just be dealing with this situation where the x-axis is an asymptote. We will get close to it as x gets negative, but we're never going to actually cross the x-axis. Y is 0 axis. So that's our introduction. And then a slightly more complicated situation is if they give us a negative power. So if we think about if we had y is equal to a half to the power of x, well, we can simplify this down and use our rules of indices on page 21. We see if we have 1 all over 2 to the power of x, that would be same as 2 to the power of minus x. Well, what's going to happen here is effectively we're almost going to mirror ourselves in the y-axis, and we are going to end up decreasing. So as when x is negative, we effectively have our positive situation. So when x is negative, when we had x is minus 1, it was like we had the original function at x is plus 1. So it's effectively like it's mirrored in the y-axis. And we are going to start off with our negative x values being input. It's going to give us positive inputs or positive outputs in our function. And we're going to end up with large numbers here as we have large negative x values being input and then being swapped into positives by the minus. And then when we get into positive x numbers, we're going to have things like when x is 1, we'll have 2 to the power of minus 1 is a half. When x is 2, we're going to have 2 to the power of minus 2, which is a quarter. So as x becomes more positive, we're going to get closer and closer down towards the x-axis. But again, the x-axis is an asymptote. We're never actually going to cross it. But again, this is what our note points out here. You can see for all of these basic functions, we end up with crossing the y-axis. The y-intercept is always going to be 1. But if we had a situation where we had some constant, if we had 5 multiplied by this function, well, what effect would that have? Well, it might make it change more abruptly, perhaps, but more importantly, when x is 0, we would have y is equal to 5 by 1 is 5. So our constant that multiplies any exponential function is going to give us the y-intercept. Now, in principle, they could go one step further in complication and say that if you had the exponential plus some constant, then the y-intercept, if we had x was equal to 0, this would be k, y would be equal to k on 1 plus c. So we would end up with 0 on k plus c as being our y-intercept. But we can work that out as we've done more practice with these. Now let's put all of this into practice with a question here. If I clearly have a positive exponential function. I'm rising up like this. I have a positive exponential function in the form y is equal to a multiplied by this big dot here means dot product or scalar product, and it is one of the ways that you can see multiplication written for these types of functions. So a multiplied by b to the power of x, and I want to find the values of a and b. Well, finding a is very easy. We effectively go to the initial conditions when x is 0, because when x is 0, I will have b to the power of 0 is 1. So when I have 0, 3, I will have y is equal to a dot bx. You can also use brackets for this, so this could just as easily be written as abx. So we can sub in x is 0, y is 3. Any point on the curve must solve the equation. This is a core point, a key point with functions and equations. So this point solves this equation. A multiplied by b to the power of 0, which is just 1. So this is a on 1. Therefore, a is equal to 3. So that part is sorted. We now know that y is equal to 3 times b to the x, which again you can use in brackets for multiply if you prefer. Now, how are we going to find b? Well, we have to be given at least one other point in order to find b, and again we have an x and a y, 2, 12. Just to point out, I went for the initial condition first. I went for when x is 0, because that y-intercept allows me to find the number that is multiplying the exponent. So you should always find the a, the constant multiplied by the exponential, first, like we did here. And then if we have a second point, we can sub it in, and that's going to allow us to find our value for b. And this style of question can come in quite an English type way. It can be quite a word heavy question, or it can be a more graphical question like we've gotten it here. But in either case, you'll find the coefficient almost always first, and then your number that has the power on it. So let's sub in here. Again, any point on the curve must solve the equation. So it must solve this equation. So 12 is equal to 3 dot b to the power of 2. So then we rearrange to get the variable by itself. We get 4 is equal to b squared. Then get the square root of both sides. So we have plus or minus 2 is equal to b. Now, we do not deal with situations where we have negative numbers to powers. They're not a well-defined function. They jump all over the place. They have a lot of discontinuities in them. So the only version of that we are interested in is b being equal to 2. So just take the positive value for these types of situations. That will be true in general for our course. So 3 times 2 to the power of x is our original function. And that is pretty universally how we can solve that type of problem. And that's what we need for now.